Thanks, Jason. So I will talk about the CancerLocator. That's a software we have recently developed in order to harness the diagnostic potential of cell-free DNA-seq. So as we all know, the cancer is a major killer of humankind. And probably the best way to reduce the cancer mortality is early detection of cancer. We all know that, if a cancer is detected early, then this patient has a lot more chance to survive. In fact, if the cancer is detected in the stage 1 or 2, the patient has a 90% chance to survive 5 years. However, if the patient is detected with cancer in the later stage, then there's only 15% chance to have 5-year survival. So in order to have the early detection of cancer, we think that non-invasive screening is a key. Because usually in the early stage of cancer, there's no symptom. And people would not want to pay a cost to have invasive diagnostic done. So for the non-invasive screening, blood-based test would be an opportunity. So as you can see, in the blood, you have various fractions. On the top, there's plasma, and that's white blood cells, and that's red blood cells. In the plasma, there's so-called cell-free DNA. So when cells die, they don't just disappear. They actually leave trace with cell-free DNA that's shaded into the bloodstream. So in the bloodstream, there's cell-free DNA is from various organs. And if some organ has a tumor, then you will see tumor DNA there. But usually, the tumor DNA fraction is very low. So the cell-free DNA in the bloodstream is a mixture of the normal DNAs, the DNAs from normal cells, and also a minor fraction of the DNA from cancer cells. So I think the cell-free DNA in the blood is like a message in a bottle in the ocean. There is a message, alarm message sometimes, for different organs' health that's embedded in cell-free DNA that we can discover for diagnostic purpose. So in this work, we focus on the DNA methylation profiles of cell-free DNA for cancer detection. In fact, we can not only detect cancer, but also locate cancer. That's because the DNA methylation actually is tissue-specific, so we can predict the cancer site from the DNA methylation pattern. And also, the DNA methylation actually has a pervasive nature, which means if some base, like CPG site, has a methylation pattern is methylated, then usually it's not only just this site is methylated, it has a spread region, covering this site, a large region is methylated. So therefore, this pervasive feature actually can be used for signal amplification in order to reduce the diagnostic cost. And also the demethylation, its abnormality occurs early in the cancer pathogenesis. Therefore, it's a good candidate for the early detection. So our method have 2 stages. So the step 1, in stage 1, we build features. By comparing the healthy plasma DNA's cell-free DNA methylation pattern to the TCGA tumor data, various TCGA tumor data in the solid tissues, methylation data, we can identify features. So those CPG sites or CPG clusters that has variable methylation patterns across different tissues, in different types of cancer. So once we have this feature set, and in the second step, when the patient has plasma comes in, so we isolate its cell-free DNA and perform methylation profile, and then using these features, we build this machine learning approach, statistical approach, to predict the cell-free DNA fraction and also the tumor type. So for the feature selection step, we select those CPG clusters if the range of their methylation levels in all tissues are sufficiently large, so they are sufficiently variable. And usually, we look at this methylation, we define the methylation level with a beta value. The beta value is basically a number of cells that are methylated in this CPG site divided by the total number of cells. So it's a population average value. So here we define the CpG cluster instead of CpG site because we want to have a low sequencing, coverage. So, in the clinical applications, so that we can use the pervasive nature of DNA methylation to group the neighbor CpG site together, so that we can reduce the cost of the sequencing. And we select this over 14,000 CpG site as informative CpG clusters, and whose methylation ranges are more than 0.25. So the beta value, the methylation value, is between 0 and 1. And we select those CpG clusters that has variable methylation. If the methylation range is more than 0.25, which is selected. And then for each CpG clusters, we model the methylation level in patients with the same tumor type to follow a beta distribution. So that is to take into account of inter-patient, inter-individual, this methylation variation. So the beta distribution is determined by two parameters, alpha and beta. So if the alpha and beta are different, it has different shape of this beta distribution. And you can see this is the normal plasma's beta distribution for a particular CpG site or CpG cluster's methylation value, and that is the distribution for the methylation levels for the solid tumor tissue, for tumor type T, for example. And for the step 2, to detect and locate cancer, we use the beta distribution that we just constructed from the training data to deconvolute a patient plasma cfDNA into the normal plasma cfDNA distribution and possibly a solid tumor DNA distribution of a specific type. And we consider here inter-individual variation methylation level by using beta distribution. And we also consider the uncertainty of cfDNA bisulfite sequencing data. The number of the reads on that side get methylated, and also the number of reads covering that side. And we use a binomial distribution to model this relationship. So the intuition can be seen very clearly. So you have here the beta distribution for a CpG site, and then you have a beta distribution for the same CpG site from the tumor type T. And you can see this two distribution can mixed by the tumor fraction, tumor DNA fraction theta. Then you can see, the final, the methylation level is basically 1 minus theta multiplied by the normal plasma methylation level V plus the theta multiplied by the tumor type T's methylation level at this CpG site U. And then when theta's value are different, you got different distribution, right? And the purpose here, the goal is that if given by this distribution, we try to deconvolute into this and that distribution. And here's our Bayesian published model. So we have two variables to determine. So what tumor type T and what tumor fraction theta, tumor DNA fraction in the cfDNA. So given our tumor type T, so we have already learned the parameter alpha beta to determine the beta distribution, and then therefore to determine the methylation level at this CpG site K. And then this normal plasma's beta distribution parameter determines the normal plasma, the methylation value K, Vk. And then based on the theta, the tumor burden, so we get finally this mixed the methylation level in the blood, And then what we observed is the methylation, the reads on that in those reads, the CpG cluster K got methylated among all the reads N. And that actually follow binomial distribution, while these two follow beta distribution. And we can formulate this goal to infer the ctDNA burden and the tissue type T to be a maximum likelihood estimation problem. And basically, we estimate to maximize the probability by given the theta and T, to observe the value MK and NK. So, and because we consider all the CpG clusters independent, so we can actually, multiply all this, probability for the K, different CpG clusters. So here's the input of the of the method. So we already learned all the methylation features for different tumor types and for healthy plasmas. And given the patient blood, So the first thing we'll do is to generate the whole genome bisulfite sequencing data. And from this raw data, we perform read mapping and methylation color, and then we get the aligned sequencing reads and their methylation states. And these two information as input for the CancerLocator, the program. And finally, what we get is a report of the tumor burden theta, tumor type T, and likelihood ratio of which tumor type which is finally determined. So here's a performance evaluation use simulation data. So we'll generate simulation data by computation mixing the entire methylation level profiles of a normal plasma cfDNA sample and a solid tumor sample of various different type of tumor, and at a very ctDNA burden. So the advantage of simulation is that we can determine the tumor burden and then to check whether we did the correct prediction. Because in the real data, you never know what is real, tumor fraction. But in the simulation data, we can really check whether we can precisely predict the tumor burden. And obviously, for the normal plasma sample, we should have ideally predicted tumor burden 0. And you can see actually in majority case, we did predict the tumor burden 0. So this is a predictor ctDNA percentage in all the normal plasma. But also, we actually have a minor fractions of the normal plasma sample for which we predict the tumor burden is probably 5% at most. So we count this as incorrect prediction. However, realistically, we feel that even in the normal population, probably there are people who probably have some features of the tumor epigenetic pattern, especially because the epigenetic pattern is very dynamic, and cancer pathogenesis is also a fluid process. And now we can check whether the predicted theta and the real theta are consistent, the predicted tumor burden. And we actually got a correlation 0.975 is pretty good result, we feel. And actually here the blues are all finally correctly assigned the tumor location, and the red not correctly assigned the tumor location. And you can see if the tumor burden is high, it's easy to assign location. But if the tumor burden is very small, tiny, then it's still difficult to assign. So we compare our method to two popular machine learning methods, supported vector machine and random forest. And we actually exhaust all the parameter space to choose the best parameter for each method and then compare the results. And we can see that when tumor burden is very small, like 0 to 0.1, that's only below 10% of tumor burden. Actually, CancerLocator, the error rate is 0.25 in this range. But the random forest and SVM, the error range is almost 80%, 75%. That is, if we just look at the blood as a whole, cfDNA as a whole, it's really not easy to distinguish the cancer signal out of the, real normal, distinguish that. But the good thing is the CancerLocator is actually doing the deconvolution process. So, and then we, after deconvolution, it's much more easy to distinguish the tumor signals from normal. So let's see the prediction performance on the real data. We have about 80 real plasma samples, and we also generate our own plasma data on the lung cancer. So we choose 75% of solid tumor sample and healthy plasma cfDNA samples as a training set to learn features, and all other cfDNA samples from the testing set, for which we apply the CancerLocator algorithm. And we can see that we have 25 out of the 29 liver cancer patients are early stage, and 5 out of 12 lung cancer patients are early stage patients. So we see how we are doing with the early stage cancer diagnostics. So this is a confusion matrix of prediction results on the real plasma data. So we do 10 times cross-validation. And you can see that, for the liver cancer, we're actually doing pretty well, not only, to assign the location. Actually 100% has been predicted as cancer, and about 80% is predicted as liver cancer. So, but for the breast cancer, we actually did not do very well, because the breast is not well circulated, and liver and lung, for which we did a pretty good job, it's a well-secreted organ. So basically, if the organ, the cells secrete a lot of cfDNA into the bloodstream, so we can more easily to identify the cancer signal from that organ. And obviously, so our method perform much better than the random forest and SVM, considered error rate. And you can see that in general, if ctDNA burden, just tumor DNA burden is high, then we can more easily predict the tumor tissue. For example, breast cancer, if the tumor burden is high, we can identify them as breast cancer. But if tumor burden is very low, then it's not easy to identify. And the same for liver cancer. In general, liver cancer, even in the early stage, you can expect 10% of the cfDNA could be from the liver tumor. So therefore, it's so much more easy to predict. So out of the 29 liver cancer sample, 25 are from the early stage, and 80% of them have been classified as liver cancer, and all of them were detected as cancer samples. And out of 12 lung cancer samples, 5 out of them are from early stage patients, and 4 out of them, the 5 were correctly predicted as lung cancer. So that's the results of CancerLocator. And we also developed an upgraded version. So we actually developed recently a more powerful version we call the cancer detector that can identify the abnormal DNA methylation signal ultra-sensitively, so much more sensitive fashion. So let me show the intuition of this method. So here you have 100 methylated reads. So this solid circle means methylated, and this circle means unmethylated. So as I mentioned, the beta value is usually what we define as methylation value is actually a population-wide. This percentage of the those reads that are going to methylate on one particular CpG site. So as you can see, the beta value for all of this site is 1, right? And because the methylation is actually pervasive, have the pervasive feature, so therefore you would expect in the same read, if this would be a read. In this same read, if one CpG site has methylated the signal, then other CpG site should also be methylated. So you can see the beta value is 1 because across 100 methylated reads, they are all methylated. Now, if there is one unmethylated read in this read population, simulate that the cfDNA scenario. So you got 1% of the DNAs are tumor DNA, and tumor DNA are not methylated. So the beta value is changing from 1 to 0.99, right? So that is very hard for us to capture the signal from 1 to 0.99, right? Use beta values everybody's using. So, but we discovered there's a feature that we should use is the pervasiveness. And we define an alpha value. We define the alpha value is not the vertical, but the horizontal. So for every read, we define its percentage of methylation. So then you can see for this cancer read, tumor DNA read, it's 0%. While for the other read, for the normal DNA read, it's 100%. So the signal, the differentiation is from 0 to 1 instead of 0.99 to 1, using this alpha value. We define this as alpha value. So based on this intuition, we have upgraded the method, and the key is to jointly model the CpG site in a read. And here is that we, as usual, we identify the markers, and then given the cfDNA methylation data. So right now, in this method, we actually assign every read a probability to come from normal or come from a particular tumor, for example, liver tumor. And so it's actually, a read-based method. And we can see the simulation result using the cancer detector. So this is a true tumor burden predicted, and that true tumor burden, and this is the predicted tumor burden. And you can see that with sequence 2x, only 2x coverage whole genome. It's actually very cheap, only $250 will do that. you have this kind of the relation between the predicted tumor burden and true tumor burden. And in fact, with a coverage 2x, so we can detect the cancer if the tumor burden is more than 1%. And in the tumor locator, previously we have to have be more than 5%. And if the coverage is 5x, we can detect the tumor if the tumor DNA is only 0.3% in the whole, cfDNA population, while CancerLocator, has only 3%. So if we do a coverage 10x, so we can stably detect the theta, tumor burden if the tumor is 0.3% of tumor DNA there. And you can see also with the increase of coverage, you get a better, prediction of tumor burden. And for the real data, we test on the liver cancer samples. And we can see that in the CancerLocator, when specificity is 100%, the sensitivity is 74%. With cancer detector, the specificity 100%, the sensitivity is 95% sensitivity. And for the 25 early stage cancer samples, when the specificity is 100%, the sensitivity is 94%. It's slightly dropped only. So we think that is actually this real data, the sequencing coverage is only 1x to 3x. So which means that we can pay like $300, $400 for sequencing. We can already get this kind of high performance for the cancer signal detection. And we found out actually that our predicted tumor burden is highly correlated with tumor size. So you can see the correlation here, 0.87. The p-value is very small. And even if we remove this, the three largest tumor size, largest tumors, we still get a pretty good correlation with 0.42. And also we can monitor actually the cancer progression. So there are 2 liver cancer patients, both did surgery, and one actually passed away shortly after surgery, and another has survived. And look at our deconvolution of the tumor burden. We can see the one survived actually have decreased the tumor burden and almost 0, but the one actually passed away has tumor burden. It's not seems like the tumor has not been completely removed. So actually, it should have also our tumor burden prediction should also have the prognostic value. Okay, in summary, so we developed the CancerLocator tool that can simultaneously infer the proportion and tissue of origin of tumor DNA in a blood sample using genome-wide DNA methylation data. And also we developed a cancer detector that can detect cancer signal ultra-sensitively at a low sequence coverage and therefore hold a great potential for detect cancer early and cost-effectively. And I want to thank the major developer for the method. Zhou has been a major developer for the CancerLocator, and Wenyu and Qingjiao have developed cancer detector, and Yonggang has generated experimental data, and Dr. Steve Dubinet's lab has provided the blood sample for lung cancer patients. And thank you for your attention.